Okay, grade 10, so welcome back. So we're going to keep moving on in chemistry. Okay, and the next topic we have to get into is compounds. So we've kind of gone through elements and kind of atoms, and now we're going to kind of talk about what most things are in the world, which is combinations of elements coming together to form a compound. So far we've been focusing on atoms and elements. That's what we've done so far in chemistry. And just a reminder, atoms are the building blocks of matter, and elements are the different kinds of atoms available to build. So I looked at some of your learning checks, and some of us still had a discrepancy between what the two terms mean. So atoms are the basic building blocks, and then the elements are the different versions of those atoms. Okay? So most things in the world are not composed of a single type of element, like a piece of copper, but rather several elements bonded together to form a compound. So we do see sometimes where there's just a pure element out there, like if you have a copper penny, or if you have a copper pipe, or you have a piece of aluminum foil, or you have a piece of gold or a gold ring. Okay? Those are elements. But most things are not that. Okay? Most things are like what you are, or a book is, or what a table is, and it's a combination of different elements coming together. So that is what we call a compound. So a compound is simply two or more elements bonded together. It can be 2, it can be 3, it can be 5, it can be 50. But it's basically several elements all bonded together. Now most compounds are not only electrically stable, so that means that they have the same number of electrons and protons, just like elements do, but they're also reactively stable, and that's a lot different than elements. Okay, elements are not reactively stable. Okay, they're actually very reactive, and they're trying to form compounds. So all elements, except for the noble gas, are striving to form compounds. If you isolate an element and it's on its own, it's not happy, and it tries to go back into a compound mode. And when doing so, they become reactively neutral and happy. So, like I mentioned, elements form compounds and become stable and to contain a full outer ring of electrons. So if we look over here at, say, oxygen, okay, we look over here at oxygen, okay, we can see that there's only 6 electrons in its outer ring. And remember, we only care about the outer ring. Okay, the first ring is filled. It has its 2 electrons, but the outer ring isn't. It has 6 and it contains 8. Well, that means that oxygen is going to be reactive. Any element that doesn't have a full outer ring is going to be reactive and trying to basically form a compound so that it does get a full outer ring. So basically, when you look at the elements, and when we did Bohr diagrams, almost every single element is going to be reactive. Okay? So when elements don't have a full outer ring, okay, of valence electrons, they will start releasing or absorbing free electrons in order to complete this outer ring. And this causes them to bond, and this is what causes them to start forming with other elements, is when they start releasing these valence electrons, or absorbing them. Now, since most elements do not contain a full outer ring, and when we drew our elements, we should have seen that very rarely do you have a full outer ring. So since most elements do not contain a full outer ring, right, this is very important, I'm going to highlight this, almost all elements are reactive in trying to form compounds. Okay? So if we look at the periodic table, all of these elements that I'm highlighting, all of these are reactive in trying to form a compound. Every single one of these will not exist on its own for long. It will start forming. Now, the exception is the last column. Okay, I'm going to highlight this in yellow. These are called the noble gases. They are the only elements that do have a full outer ring, and they will not form compounds. But everything else is actively trying to form a compound. If you have a piece of carbon, it's going to try and go and start bonding with oxygen and form carbon dioxide. Okay? If you have a piece of lithium just sitting there, it's going to react with oxygen and form lithium oxide. So these things are always trying to go back into their compound. So here's just an example. Okay, here we had water. Okay, and I'm going to highlight in red the oxygen's original electrons. So 1, 2, 3, 4, 5, and 6. Those were oxygen's original electrons, but you could see it didn't have a full outer ring. It needed 2 more. So what it ends up doing is sharing with hydrogens. And I'm going to kind of highlight in yellow hydrogens. So there's one hydrogen and there's the other hydrogen. Well, you can see when these things now form, everybody has a full outer ring. You can look at oxygen, and their full outer ring is, and I'll do this now in red. Sorry, we'll do this in blue. I've got 1, 2, 3, 4, 5, 6, 7, 8. So oxygen's happy. And then hydrogen, although it only has 2, remember only 2 electrons can go in the first ring. So hydrogen's got a complete outer ring. And this is why this compound formed. Now everybody has a full outer ring and is stable and now won't be as reactive as hydrogen is on its own or oxygen is on its own. So water is very, very reactively neutral. Okay, so elements form in compounds. Why are elements reactive and compounds generally not? Well, to explain this, we really kind of need to know what a reaction is. And all a reaction is valence electrons jumping from one atom to another. So why these valence electrons would jump and essentially form a reaction is to try and stabilize itself. So if we look over here at sodium, okay, on the right, we see sodium only has one electron in its outer ring. Okay, so it's going to want to try and kick that electron off. Okay? If it's able to basically kick this electron off out into outer space, now it has a full outer ring of electrons. Okay, because you can either kick them off or absorb them. So that's what essentially does, is sodium will kick that off. So if we look down here, sodium's going to kick that electron off. Now, chlorine, if chlorine is in the vicinity where sodium is, when sodium kicks off that electron, we look over here at chlorine. Chlorine only has 7 electrons in its outer ring, and it would like to absorb one. While sodium's going to kick it off, and chlorine's going to absorb it, and then it's going to have a full outer ring. So it's going to go there, and now chlorine will have 8. And if we look down here, here's a formation of sodium chloride, or a compound, where sodium has a full outer ring, and chlorine has a full outer ring. And they were only able to achieve that by forming a compound. Okay. So in most atoms, there's an incomplete number of valence electrons, kind of like sodium, in the outer shell, and that atom will try and fix that by reacting. In compounds, the outer shells of atoms are full, and therefore there are not any electrons available to jump. When we get down here, both shells are full, and the valence electrons will not jump anymore because they're happy. Okay. So generally, compounds are way less reactive than solo elements. Now, the importance of compounds. Why do we study them? Well, almost all of matter exists in compounds. Okay? It's very rare to find an element in nature. You can. It's very, very rare, but you can do it. One of them is gold. You can go out and basically in the ground, you can find a piece of gold. But you can't really do that with any other element, or very few elements. You can't go out and just find nickel, a piece of solid nickel, or a piece of solid copper. They're going to be in ores or in rocks. You can't go out and find just basically pure silicone or pure iron. Okay, they're all basically in compound mode. So we have to go in there and isolate them. Okay, so this is an element right here, gold. But this is not. This is what we call an element, gold. But this would be a compound, water. Okay, oxygen, gas, would be an element. Okay, salt would be a compound, and then silver would be an element. Okay, so just some examples of the two. Okay, so here's some examples of what happens once you isolate elements, because like I mentioned before, elements are super reactive. So if you isolate them, they're going to want to go back into compound mode. So here's an example of copper. So what they've done is they've isolated pure copper metal. Right? And they oftentimes will put that on roofing, and it's a very nice color, it's this kind of orangey color. Now this is pure copper. But again, copper is reactive. And over time, it will want to go back into compound mode because copper is not happy. It's got valence electrons that aren't full. So what it will do is start releasing electrons and start reacting with oxygen in the air. So what happens to these roofs over time is they react with oxygen in the air, and they turn from this orange over to this green, because this green is copper oxide. It's the fact that this was pure copper. It reacted with oxygen that's just in the air and formed copper oxide. Okay? And that's a different color. And we know that this was a chemical reaction because we saw a change of color. You remember from our unit before. Now, similarly, if we use iron, so if we isolate some pure iron, okay, or Fe is iron, okay, we have this really pure, nice metal. But again, it's an element, and it doesn't want to be in elemental form. So what will it react with is oxygen in the air. Okay, all metals react with oxygen in the air, called corrosion. And it will turn into what we see here. Well, this isn't pure iron anymore. This is iron oxide, or rust. Okay? And all rusting is, or corrosion is elements trying to go back into their compound mode where they're happy. Just a couple other examples is tarnishing. So you may have heard of tarnishing before. If you have some really nice silverware at home that are made of pure silver, we make them out of silver and gold so that they don't corrode very fast. That's one of the advantages and why gold and silver are so expensive, is because they don't react with oxygen as fast as other metals. Well, it does. Silver will still do that. It just does it really slowly. But over time, the silver will turn into what we call a tarnishing. And all that is silver reacting with oxygen to make silver oxide. And now that outside layer has this tarnish on it. Okay, and you can clean that off by scraping it off with some sandpaper, or there's some cleaners. Okay, our coins do the same thing. So our coins are made out of metal. So we make coins out of nickel. We make coins out of copper, all kinds of different metals. But over time, we have to replace those coins because they corrode. And if you've ever seen a coin that's brand new, it's very, very shiny and nice. But then over time, these things react with oxygen and start forming nickel oxide and copper oxide. And that's when the coins don't look very nice anymore. Okay. So how do unstable elements become more stable? Well, they all, like I mentioned, they all form compounds. So here's an example of a very, very common compound that we talk a lot about. It's table salt. Okay. So when we form table salt, we take pure sodium, which is a metal. Okay, and it's a very, very toxic, dangerous metal. And we take chlorine gas. Okay, and these are two elements. So sodium is an element and chlorine is an element. And when we combine these two, we make sodium chloride, which is a compound. Okay. Now, this is the interesting thing, is when these things combine, they're unlike their original at all. Okay. Oftentimes we think, okay, if I take blue, let's say if I take some blue paint and I take some green paint and I mix them together, they're going to be kind of half blue, half green. It's going to be a mixture. It's not like that in elements. If I take sodium and I combine it with chlorine, okay, and if I look at, say, the properties of sodium, so sodium's a metal, it's toxic, it's solid at room temperature, it reacts with water. Okay? Chlorine gas, toxic, it's a gas, it forms hydrochloric acid with water. If I look at all these different properties, when I combine them into table salt, it doesn't contain any of those properties anymore. So table salt's not poison at all like sodium or like chlorine. Right? Table salt's not metallic like sodium, or it's not a gas like chlorine. When you combine two elements together and it makes a brand new compound, it's nothing like the originals. It's not like it contains any of the properties of the originals. It makes a brand new piece of matter that has its own properties, okay? And nothing like the original properties of its buildings. Okay, so here's some general bonding rules. When things are going to come together, because you can't just kind of throw any elements together. There is some rules to it. One, and it's simple because there's only 3 rules. Okay, metals usually form bonds with non-metals, and their compounds are always solid. And metals usually don't like to form with other metals. They usually like to form with non-metals, okay? And then they're going to make a solid. Non-metals, so something like oxygen, can form bonds with metals, like I mentioned in the first part, as well as with other non-metals. And they can form solids, liquids, or gases. So that's like water. So hydrogen's a nonmetal and oxygen's a nonmetal, and they can form together to make not only solids, but liquids and gases as well. And then the last one, the only elements that are never found in a combined form are the noble gases. All the other elements are always going to be found in compounds, but not the noble gases. They can't be found in. So just some very popular compounds that we should know about as a chemist. Like I already mentioned, this is table salt, sodium and chlorine combined. This is carbon dioxide. So this would be 2 nonmetals combined together. And then down here is fertilizer called ammonium nitrate. So ammonium is NH3, nitrogen and hydrogen combined together. NH4, we call that ammonium. And then the NO3 we call nitrate. So when nitrogen combines with oxygen, we call it nitrate. So together, that's ammonium nitrate. Okay, so then just kind of identifying, when we look at a formula for a compound, recognizing what that means. So when we say NaCl and there's no numbers down here, that really means that there's a 1 down there. So there's 1 sodium and 1 chlorine in this compound. In this compound over here, this is reporting that there's 1 carbon atom, and that's this black thing right down here. And then we have 4 hydrogen atoms attached. Okay, and this would be called methane or natural gas, if you've ever heard of it before. And then H2O down here, this is telling me that I have 2 hydrogen atoms and 1 oxygen atom. All right, so the different types of compounds. This kind of comes down to our rules. There's not that many different types of compounds. There's actually only 3, and really 2 clear ones, and one's really not a compound. So although there are millions and millions of potential compounds, chemists have classified them into only 3 groups. Because if we look over here, everything in red are my metals, my blue are nonmetals. Okay. And then the yellows are called metalloids, don't worry about them. But if you look at it and we kind of say, okay, let's ignore metalloids, there's really only 2 things. There's metals and nonmetals on the periodic table. So those are the only 2 things we can combine. Well, what if we take a metal that's red and combine it with a nonmetal that's blue? That's what we call an ionic compound. And that's what we're going to start with, and we're going to kind of focus in on this unit. So that's one thing you do. You take a red and you combine it with a blue, or a metal and a nonmetal. Now, what if I just take 2 blues and I don't even use a red? Well, that's what we call a covalent compound. It's when you take 2 nonmetals and you combine them together, like water. And one that we don't really talk about in this course, but you can be familiar with, well, what if I just take 2 reds? And those are called alloys, or metal alloys. And they're really not a compound because they don't really kind of do the same things as the first 2. But you should know about them. We don't really talk about them too much, but they're called metal alloys. So that's be something like what steel is. So steel is several metals combined together. Or a lot of your jewelry are kind of metal alloys. Okay, and that's it for kind of the introduction to compounds and the different types of compounds.